In chapter exercise 2, here we go. So x squared plus x plus 1 equals to 0, then the value of x plus 1 upon x squared plus x squared plus 1 upon x squared and so on. Okay, so right, x squared plus 1. Okay, that's not nice. What can we do with this thing? It's gonna have n and stuff like that. That's not nice. Well, first of all, just write it as summation. So summation of, it's all gonna be squared, so x power r plus 1 upon x power r squared, and it's gonna go from r equals to 1 to 27. So it's summation of so from 1 to 27 of x power 2r plus 2 plus x power minus 2r. Okay, cool. So summation from 1 to 27 of x power 2r plus summation from 1 to 27 of x power minus 2r plus, what do we have? Just 2. So from 1 to 27 numbers, so 2 times 27, which is 54. Okay, so now what? So x power 2r, we know that x has to be a root of this equation, which means it has this identity that x cubed equal to 1. All right, and so now what? X power 2r, you say that also in fact is a root, right? Yeah, so if x is omega, x power 2, that's gonna be omega squared, but that's still just another root, so we can replace it with that and it will also work, right? Because squaring both of them, they give like the same thing. So yeah, that's nice. So what does that mean? That's like if omega is, does that make sense? So omega squared, one of them is gonna have twice the argument. They are not conjugates or anything, but when then we double them once again, oh yeah, this gonna be in a triangle kind of situation, so that's why it's gonna work. Right? So in fact, yeah, they are conjugates. So twice the argument, right? That leads to still the same thing. Yeah, that makes sense. Correct. Or does it? Whatever. We do have x cube equal to 1, so we can simplify this. Okay, so it's gonna be like x power 2 plus x power 4 plus x power 6 plus x power 8 and so on, right? So x cube equals to 1, so we can write as x squared. In fact, x, should we write like, nah, just gonna write like this, plus this is gonna be x plus, well, it's gonna be x power just 1, so 1 plus x squared plus, well, you see this, it's gonna repeat itself, so it repeats in a chain of 3. So 1 to 27, there are exactly 9 chains of 3, so it's gonna be 3 times of this thing, 3 times of x, sorry, 9 times of x squared plus x plus 1, because then I start with this thing and eventually you're gonna end with 1. And guess what, this thing is just 0 because that's given to us, so it's just 0, it's completely gone. And I guess similarly we can do for that as well, so it's gonna be negative as well, so just negative 1 plus 1 over there, so 9 of, well, x power negative 2 is just 1 upon x squared plus 1 upon x plus 1. Now I can write this thing as x cubed, this thing is x cubed as well, so 9 of this is x squared plus x plus 1. Guess what, this also cancels. So yeah, these two are just gone. You got this as the answer. Easy. So it's gonna be 54. Was there some other easy way for this though? You're getting x plus 1 upon x and x squared plus 1 upon x. If you just square that, well, maybe no, maybe that wouldn't work. Yeah, whatever. So 54 is the answer. Next question. Sum of common roots of the equation z cube plus 2z squared plus 2z plus 1 equals to 0. Hey, I think I've seen this format once. So this is actually kind of factorizable. So z cube plus z squared plus 2z plus 1 This thing is just z plus 1 squared. This thing is z squared into z plus 1, I guess. So z plus 1 into z squared plus z plus 1. Hey, wait a second. So yeah, fine. That's for this equation. What about this equation? Z power 1985 plus z power 100 plus 1 equals to 0. Wow, that's not nice. 1985. Okay, that's gonna have 1985 solutions as well. So no, that's not doable. That's obviously not factorizable, right? But what do we know? So we want common roots. So this is exactly 3 roots. So just gonna check for each root. Yeah, so this gives 2 roots, two cube roots of unity, and this gives -1. Is -1 a solution? It's not. So this identity, we can use that to simplify this maybe. So from this you can say z cube equal to -1 is equal to 1 is true all the time. So z cube equals to 1, right? So if z is a common root, in that case 1985 can be written as 3 into, it's gonna divide by 3, so 5, sorry, 6 is 18, 1 is 3, 2. Okay, so 661 times 3, all that doesn't matter, so it's gonna be z squared plus, so 99 plus 1, it's gonna be z plus 1 equals to 0. Yeah, that works really nice, which means that in fact both of these both of the roots from this equation, that will be 0, that will work. Both of these are common roots. So what's the sum of the common roots of the equation? It's going to be minus b upon a, which is -1. That's the thing. Next question: which of the following is equal to cube root of -1? Cube root of -1, you say. So x cubed equals to -1. Okay, so they give in some weird format though. All right, I guess we just need to find them and then see which of them matches. So x cubed plus 1 equals to 0, so x plus 1 into, okay, so one thing will be -1. Is any of them -1? Square root of 3 plus iota upon 2 iota. No, that does not look like -1. This does not look like -1. This does not look like -1. Nope, none of them are -1. Right, so this is discarded. You just have this thing. So x equals to -b, so plus 1, square root of b squared, 1 minus 4 is like -4 upon 2, which is 1 plus minus square root of 3 iota upon 2. Nice. So square root of 3 iota, right? So it should be having that. Well, is this gonna work? Is this square root of 3 plus iota? No. Oh yeah, okay, wait, just might work. It's like divide by iota and stuff, or maybe like multiplied by iota squared upon -1. Okay, but iota squared does not help. It doesn't help to cancel this thing, so we need to multiply by iota, but that, yeah, that won't work. So it's not correct. This is not correct. Square root of 3 minus iota upon 2 iota, maybe that will work. This is negative iota. Well, no, that's not gonna work. So you got these options. Let's see which of them matches. So this thing is square root of 3 minus iota upon 2 iota, which is, so square root of 3 upon iota, it's gonna be negative 1 upon iota, is like negative iota. So negative iota square root of 3, and then -1 upon 2. Is this? It's not in the solutions. Nope, doesn't work. What about this guy? So negative square root 3 plus iota upon 2 iota, which is, so this is gonna be iota square root 3 plus 1 upon 2. Hey, yeah, that's in the solutions, so this is gonna work. Next question: 1 plus x equals to 2 cosine a, then x power n plus 1 upon x power n. Yeah, I've seen this somewhere. I don't remember where, but I've seen this. So it's from a recursion, I guess. The only real solutions would be x equals to 1 and cosine a equals to 1. But and yeah, and x equals to minus 1 and cosine a equals to minus 1. Other than that, it has no real solutions. But still, let's try it for this thing, for complex solutions basically. So we are going to, okay, so this is for nth power. Well, that is not nice. The nth power, so like you have to raise this to the nth power. Well, let's do it. So 1 upon x plus x to the power of n, that's basically 2 power n cosine of a to the power of n as well. Was there something else that we could do? Yeah, if n was 2 power something, we could do the recursion thing, but other than that, what? No, it doesn't work like that. It's got something. Oh, right. Very nice. Right. So yeah, let x be equal to e power something. So e power okay, wait a second. What if you got r over there as well? That's not good. What? Okay, fine. What if it has r? That won't work. You know what? Let's just make a quadratic and see what we get. So it's got x squared minus 2 cosine a x plus 1 equals to 0. So x equals to minus b, so 2c plus minus square root of b squared, square root of 4c squared minus 4 upon 2, which is c plus minus square root of c squared minus 1, which is c plus minus I sine. Hey, that was nice. Yeah, so we could have got that either way. So yeah, cosine plus minus I sine. So then this thing is equal to, all right, so that thing to the power of n, right? That's, hey, that's nice. We know that. So x power n just multiplies by n, so it's gonna be nc plus minus isn, whatever that thing is. Okay, and multiply by minus n as well, so minus nc minus plus isn. Yeah, that looks correct. So this cancels, she's got 0 as the thing. Well, no, but that should not be correct, right? Plus x power negative n. Yeah, no, that is not nice. That's not nice because that was not the thing itself. Oh, come on, that's not the thing. That's just not the thing. So x power n, so it's theta no, a. So x power n, that will be cosine of na plus minus I sine of na. Come on, what am I doing? And for this is going to be negative n, so it's going to be cosine of negative na plus minus I sine of negative na as well. Guess what? This cancels, and this thing is the same as that thing, so it's going to be 2 cosine of na. There we go. Okay, next question. Alpha plus iota beta equals to tan inverse of z. Z is x plus, okay, the locus of z is, all right, well, fine. So first of all, tan of that, so tan of alpha plus iota beta, that's not nice. Do we know how to calculate tan of complex numbers? I guess we do. Yeah, it's not that hard because we know that cosine of theta is e to the I theta plus e to the minus I theta upon 2, and sine theta is e to the I theta. Hey, it was different. Minus e to the minus I theta upon 2i. Okay, yeah, which is like minus over there, and then you just got I over there. Okay, that's nice. So now what? Tan theta. Tan theta is just upon that. In fact, let's just keep that over there as well. Nah, let's just do it like this. It should be negative e power I theta minus e power minus I theta iota upon e power I theta plus e power minus I theta. So this should be negative. Right, so now we can calculate tan of stuff. Cool. So tan of alpha plus iota beta. Okay. Oh god, it's gonna be really bad. Okay, but we cannot try it. First of all, written as e power 2I theta minus 1 upon e power 2I theta plus 1 iota. So tan of alpha plus iota b iota beta, this should be negative. So e power 2 times of whatever this argument is, no, whatever this number is. So e power 2 alpha times, wait, no, sorry, alpha I e power negative, yeah, negative 2 beta. Oh, so that's why this negative is there, to balance that, minus 1 upon e power 2 alpha I e power minus 2 beta plus 1 iota. So this should be, now we can just put that negative there and do that thing. So it should be e power 2 beta minus e power 2 alpha iota upon e power 2 beta. Okay, minus e power 2 alpha iota. How long is this going to go? This is really long. There should be a simpler method, but whatever. Now what? Multiply by the conjugate of this. Oh no. Okay. So yeah, I don't want to be doing that. Wait, did we just get minus over there? It should be plus. It should be plus over here. And this thing is equal to x plus iy. Right. What should I do? That won't be working though. We do need to use Euler's theorem to expand this because there's no other way. But then that will give us kind of an asymmetric value. That's not nice. Think there's no conjugates over there, and it's not like that. It's gonna be the same thing over there. It's just gonna be... but then you just have to do it. There's no other way. Okay, let's just do this. Just do this. Who knows? It might just work. So e power 2 beta plus cosine of 2 alpha minus I sine of 2 alpha upon e power 2 beta iota times all of that, right? Plus cosine of 2 alpha plus I sine of 2 alpha. So multiplying by the conjugate of this thing, just get I times e power 2 beta plus cosine of, right, it's not, it's just too big. Then how do I make it work if that's not the way to do it? Alpha is a constant, the locus of z is, hey, so alpha is a constant and beta varies. Okay, but they didn't give us what kind of constant it is. For all we know, it's just a constant over there. One thing, what can we do? Divide this quantity by iota and then component it divided into, I mean, like, yeah, you can actually cancel that from that, but that's not the best way to do it, right? Okay, so what if I get that over there and then yeah, maybe that is better. So I'll try that, and if it doesn't give us the result, we just move on. So x plus iota y, divide this by iota, so this should be negative iota x plus y equal to this thing. So I'm gonna solve for e power 2 beta. e power 2 beta into this thing, so negative iota x plus, wait, no, just that, just this much, uh minus 2 minus e power 2 alpha I equals to e power 2 beta times all of that, so it should be e power 2 beta times minus I x plus y plus e power 2 alpha I times minus I x plus y, and then that goes over there, so e power 2 beta 1 minus y plus I x equals to e power 2 alpha I, and then that goes over there. Alright, so it's gonna be 1 over there, so 1 plus y minus I x. Okay, fine. So e power 2. Did I just mess something up? It should be plus over there, so this is definitely correct. Yeah, I didn't mess that at least. Hey, we could have written it in that form as well, right? So no, but that would not work. So this should be the thing, so just goes over there, right? So this e power yeah, so it's gonna be the 1 minus y plus iota x, it's e power 2 beta, and now we can use the cosine I sine on this guy, so cosine of 2 alpha is I sine of 2 alpha times 1 plus y minus ix, and then we can solve, and this is a real value, so it's gonna eliminate for that, which means you don't want any iota thing anywhere, or at least you want that to be equal and stuff. So yeah, so let's do this. It should be equal to, you got minus, no, it's just equal to over there, cosine of 12 into 1 plus y minus plus sine 2 alpha x plus iota times, so this thing can be anything that we want, right? No, it must be a particular value, so fine. So that's gonna give us two equations, and then we need to solve those equations, and that will give us the solution. No, it's just too big, it's impossible to solve it like that, there must be some other way. Whatever, next question. Okay, so 1 minus iota 1 plus iota to the power of 100 equal to a plus I. Okay, then right, so this thing is e power minus pi by 4 upon, so that is gonna be minus pi by 2 over there for this whole thing, to the power of 100, right? So e power minus 50 pi, which is cosine of minus 50 pi, well, that is, it's an even number, which means it's gonna be 1, and sign does not matter, so a is 1, b is 0. This could have also written like that. Yeah, so 1 minus iota squared, that will give the real part to be 0, and that's why it's gonna get a purely imaginary number to the power of 100. Well, that gives a real number, in this case 1, so a equals to 1, b equals to 0. Next, xr equal to cosine of pi upon 2 power r plus I sine of pi upon 2 power r, then x1 x2 x, okay, so multiplication of all of them is yeah, it's easy, so just e power I pi upon 2 power r, so we want to multiply all of these, so that means e power I, the summation of this thing, pi upon 2 power r, 2 power r, not 2 r, and it goes from r equals to 1 to infinity. Okay, so e power I, you got pi over there, and this is like 1 by 2 plus 1 by 4 and so on, so we know this thing is just 1, so it's just gonna be e power I pi, which is minus 1. Yep. Hey, this is the Euler's identity. Whatever, next question. ZR is, hey, it's the same thing. It's the same thing. Okay, fine. So ZR is just e power iota r alpha upon n squared. Okay, fine. And then you just want to sum these from 1 to n. So multiplication of all of these is just e power I. And then you got sum. Well, r is varying, alpha and n squared are not varying. So alpha upon n squared, and then the summation of r, I believe, from 1 to n. Yeah, that seems legit. And yeah, n approaches infinity. Well, we're gonna do that later. First of all, just find this summation. So from r equals to 1 to n, that will be n into n plus 1 upon 2. Okay, and now n approaches infinity, so that means that this complete thing, it approaches 1, so it is gone. So just e power I alpha by 2, which is cosine of alpha by 2 plus I sine of alpha by 2. Yep, next question. 1 plus sine theta plus I cosine theta upon 1 plus sine theta minus I cosine theta to the power of n. Have I seen this somewhere? Maybe. Yeah, well, in fact, I have seen this somewhere, right? Oh yeah, so 1 plus sine, right? So 1 plus cosine of pi by 2 minus theta, so that thing can be written as 2 cosine squared of pi by 4 minus theta by 2. And then this I cosine of theta by theta, that thing is basically I sine of pi by 2 minus theta, which is 2I sine of theta by 2 cosine of pi by 4 minus theta by 2. When you divide this cosine factor, it just cancels. So in fact, this 2 factor also cancels. So you just get cosine of pi by 4 minus theta by 2 plus right, yeah, plus I sine of pi by 4 plus theta minus theta by 2. And then the same stuff, just negative over there. So it's going to be e power this thing, so pi by 4 plus theta by 2 upon e power negative of that thing, because yeah, so minus pi by 4 plus theta by 2. So this is going to be e power pi by 2 minus theta I times all of that stuff. Okay, yeah, that's nice. So cosine of pi by 2 minus theta, wait, that to the power of n, so this to the power of n, so it should be n times of that. So cancel this. Cosine of n pi by 2 minus n theta, this looks familiar, plus sine of n pi by 2 minus n theta iota. Okay, is this in the options? N pi by 2 minus n theta minus, hey, that's the first one. Yeah, next question. If the cube roots of unity be 1, omega and omega squared, then the roots of the equation x minus 1 cube plus 8 equals to 0 are. Alright, so that means x minus 1 cube plus 2 cube, right? So you know what, no, x minus 1 upon 2 cube plus 1 equals to 0. Yeah, that makes sense. So this thing, x minus 1 upon 2, it has the roots 1, omega and omega squared. Easy, right? Wait a second, just wait. No, cube roots of unity, right? So it should be negative 1 over there. Oh no, negative 1, that's not nice. Yeah, so negative of that thing, that will work, I guess. So this can be written as, so that goes over there, it becomes minus 1, and that goes over there, it becomes plus 1 minus x upon 2 to the power of 3 equals to 0. So now this yeah, this quantity will have the roots as 1 omega and omega squared. So 1 minus x upon 2 equal to 1 omega or omega squared, which means 1 minus x is 2 omega or 2 omega squared, which means minus x is 1 2 omega minus 1 or 2 omega squared minus 1. So x is minus 1 or 1 minus 2 omega or 1 minus 2 omega squared. Nice. So this is wrong. minus 1, 1 minus 2 omega. This is wrong as well. This is the correct one. Yeah, next question. Omega is an imaginary cube root of unity. If 1 plus omega squared to the power of m equal to 1 plus omega power 4 to the power of m, then least positive integral value of m is, okay, okay, it's a cube root of unity, right? So it's going to be 1 plus omega squared to the power of, in fact, why even do that? 1 plus 1 upon omega to the power of m equals to 1 plus omega to the power of m. So this thing, you guessed it, it's going to be 1 plus omega upon omega. So this cancels this immediate factorization. So just got omega power m equal to 1. So m equals to 3. That will be the least value. So yeah, next question. If omega is the cube root of unity, then 3 plus 5 omega plus 3 omega squared to the power of 2. Right. Okay. That's new. Squared plus this thing. Should we just kind of expand it? No, don't do that. First of all, simplify this. So 3 plus 5 omega plus 3 omega squared. We can take this down easily, right? So this can be written as 3 plus 3 omega plus 3 omega squared plus 2 omega. So this thing is just 2 omega. So 2 omega squared plus, similarly for this thing, 3 plus 3 omega plus 3 omega squared, that's gone. So 2 omega squared is remaining squared. So this should be 4 times of omega squared plus omega power 4, which is 4 times of omega squared plus omega. So it's going to be 4 into minus 1. So it's minus 4. That's the value. Next question. If iota equals to square root of minus 1, then 4 plus 5 times of all that stuff. Okay, so 4 plus 5, what is this? It is e power, well, minus 1 by 2. That happens at, when does it happen? Pi minus pi by 3, I guess. So 2 pi by 3. So 2 pi by 3 to the power of 334. So I have times of that. Plus 3 times. What are these values really? Okay. And the same thing. In fact, wait, what? Okay. Right. So same thing. This is e power I 2 pi by 3 to power of 334. Probably something will cancel away. That's why they gave us like this. So e power iota. Well, let's see. Is this a multiple of 3? Not quite. Hey, this is 365, not 334. So it's gonna be 2 times of that, which is 668 upon 3 pi. Right, so all of the 2 stuff, well, that will get cancelled, which means you wanna divide this by 6. That makes sense. And plus 3 times e power minus, yeah, that would make sense. So this can be written as like 2 pi. Okay, that will be better. So 2 pi into what was the stuff? 334 upon 3, and this is iota 2 pi into 365 upon 3. So what's the fractional part of this guy? That's what we want. 333, that's constant. It's going to be 1 by 3. Yep. For this guy, 363, so it's going to be 2 by 3. Alright, so 4 plus 5 e power iota 2 pi by 3 plus 3 e power iota 4 pi by 3. Okay, 4 by 3 is still not quite as, okay, it's not still big. It's like pi plus pi by 3. This is pi minus pi by 3. Right. So only the thing is like sine stuff, that's different. So this is just 4 plus 5 cosine of 2 pi by 3, which is minus 1 by 2, plus sine of 2 pi by 3, which is square root of 3 by 2 iota, plus 3 of minus 1 by 2 as well, but minus square root of 3 by 2 iota. So this should be, well, let's see. So minus 3 minus 5 is minus 8. Minus 8 by 2 is minus 4. So this is just 0. for the real part is 0, and 5 minus 3 is 2, 2.2 is 1, so it's going to be plus square root of 3 iota, square root 3 iota. Cool. Let omega be an imaginary cube root of unity, then the value of 2 into omega plus 1 into omega squared plus 1 plus, alright, is, what is this question really? So what's the general form for each of them? This is going to be r, in fact not even r, it's going to be r plus 1, r plus 1 into r omega plus 1 into r omega squared plus 1. Let's simplify this, so it's going to be r plus 1, r squared omega cubed, yeah, plus r omega plus r omega squared plus 1. This thing is just 1, so r squared plus 1, r plus 1 into r squared plus 1, and then r times omega squared plus omega, which is minus r. Okay, so it's going to be r plus 1 into r squared minus r plus 1, which, oh, that's just r cubed minus 1, huh? Alright, so we're just summing up r cubed minus 1 basically. So it's just the summation of r cubed minus 1, from where to where? From r equals to 1 till n. So this part gives minus n over here, this part gives n squared into n plus 1 squared upon 4, right, which is basically this thing. So yeah, cool. Next question, the roots of the equation x power 4 minus 1 equals to 0. So x power 4 equals to 1, that means x squared is plus minus 1, so like 1 and minus 1, so x, does that make sense? Yeah. X will be, so the square root of these will be 1 and minus 1, and the square root of these will be iota and minus iota, so these will be the roots. 1 and okay, no repetition with the roots. 1 minus 1 iota minus iota. Cool. Yeah, that's it. Let's check. So 15th B, 14th what, A, r cubed, oh right, sorry. So r plus 1 times r squared minus r plus 1, that should be r cubed plus 1, so sum that up, this should give n in that case. So yeah, it's wrong, this should be the correct thing. Next, 13th C, 12th C, 11th D, wait, what, 10th C, just wait a second though, minus 1, that was the thing that we got, right? We got this x by 2 equals to 1 omega squared, so this will give 2 and then 1, so x equals to minus 1, right? What's wrong in this? What's wrong? Minus x cube, okay, that's gonna go there, fine, upon 2. Yeah, that should be the thing, 1 omega and omega squared, so this goes over there, it's got 2. So if this is the case, it's equals to 1, that 1 minus x equals to 2, so x equals to minus 1. Yeah, so I just chose B because of that, and they are saying that 10th C is correct. Well, no, you are wrong in this case. 9th A, okay, 8th C, 7th C, 6th B, 5th A. This I was not able to do, I think I'm gonna do it later. So 4th A, 3rd B, yeah, 2nd A and B, yeah, correct. Okay, that's it. I will see you in the next video.